To understand the actual mechanics of modern control systems, we are going to walk through the complete architectural framework developed by Devi Automation Solutions. On a live factory floor, you face massive, high-speed kinetic energy. Thousands of mechanical actions happen every minute, requiring absolute precision to avoid catastrophic collisions. If you strip away the steel and aluminum, you reveal the electrical nervous system actually driving that motion. Miles of copper wiring, hundreds of discrete sensors, all routing back to a central programmable logic controller, or PLC. A common assumption among junior engineers is that automation begins and ends inside a software environment, writing ladder logic on a laptop. The actual engineering challenge happens before a single line of code is written. You have to design a rigid, interference-free physical architecture capable of translating raw mechanical movement into clean, reliable electrical signals. Mastering automation requires building this entire physical to logical loop, engineering the system up from the raw power supply all the way to global SCADA networks. The bedrock of any modern control panel is the 24-volt direct current power system. This split diagram shows the starting point, the switched mode power supply, or SMPS. Factories run on highly volatile alternating current. The SMPS rectifies that unstable AC mains power into a flat, predictable 24-volt DC baseline. From the SMPS, we draw our primary distribution bus. The red positive 24-volt line and the blue 0-volt return line must be strictly isolated across the entire schematic. We also introduce a separate dedicated earth-ground path. 0 volts is the electrical return reference for the DC circuit, while earth ground safely shunts away electromagnetic interference from the high-voltage machinery nearby. Mixing them up injects noise directly into your logic controllers. Translating this schematic into physical panel layout requires strict mechanical discipline. We crimp numbered ferrules onto every exposed copper wire and route them through dedicated cable ducts into standardized terminal blocks. Without this perfectly grounded, mathematically documented power foundation, subsequent PLC logic becomes vulnerable to fatal ground loops and erratic sensor behavior. With clean power established, the next layer is getting physical sensor data from the factory floor into the input terminals of the PLC. This introduces the most frequently misunderstood concept in panel wiring, the difference between PNP and NPN architectures, often referred to as source and sink. Look at this cross-sectional diagram of a proximity sensor wired directly to a PLC input. To understand the circuit, you have to track the physical direction of the electron current, not just the voltage potential. In a PNP, or source input configuration, the field sensor supplies the 24-volt current. The current flows out of the sensor, through the wire, and into the PLC's internal optocoupler. Because the sensor is sourcing the current, the PLC terminal acts as the sink. It absorbs the incoming electrons and routes them down to the internal 0-volt rail to complete the circuit. An NPN, or sink input configuration, does the exact opposite. The internal common of the PLC is tied to 24 volts. The sensor now acts as a switch to ground, drawing current away from the controller. In this NPN setup, the PLC terminal is actually the source, pushing current out into the field device. Wiring a PNP sourcing sensor to a PLC input that is also configured to source current creates a direct conflict. Two positive potentials face each other, resulting in dead inputs that refuse to trigger. If the error bridges a ground path, you create a direct short circuit that will instantly melt the internal optocouplers of the PLC hardware. Mastering the direction of current flow renders hardware differences irrelevant. Whether you are wiring a Siemens, Delta, or Mitsubishi controller, the laws of circuitry dictate exactly how the devices must connect. Once the electrical signal successfully crosses the optocoupler, the physical voltage is converted into a logical bit. The processing now moves inward to the CPU. A common misconception is that a PLC monitors inputs and updates outputs continuously, reacting to electrical changes the exact microsecond they occur. This cyclical diagram shows the actual mechanism, the scan cycle. The PLC CPU operates in a strict sequential three-step loop. Step 1. The CPU reads the physical states of every input terminal simultaneously, takes a frozen snapshot of those values, and locks them into memory. Steps 2 and 3 happen against that frozen snapshot. The CPU runs the ladder logic from top to bottom, calculates the required results, and then universally writes all the new states to the output terminals at the exact same time. This entire three-step sequence typically completes in 2 to 5 milliseconds. That cycle time is the absolute speed limit of the automation system, dictating exactly how fast the factory machinery can physically react to a changing environment. Moving out of the CPU, we reach the output terminals. The PLC uses highly sensitive, low-power microelectronics that cannot directly handle the massive voltage and current required to spin heavy industrial motors. This schematic illustrates the solution: interposing logic. We wire the PLC's 24-volt digital output to the coil of a small intermediate component called a relay. When the PLC output turns on, the 24-volt signal energizes an electromagnet inside the relay. That magnetic field physically pulls a set of heavy metallic contacts closed, bridging a totally separate high-voltage circuit. That newly closed relay contact allows 415 volts of alternating current to flow out and fire a massive three-phase motor contactor, which finally drives the heavy machinery. The type of load dictates the hardware. We use these mechanical relays for slow, heavy AC loads. But for precise servo motors that require thousands of pulses per second, we bypass mechanical parts entirely and use solid-state transistor outputs that switch in microseconds. The output layer is an escalating ladder of power. It takes a fragile digital 0 or 1 and safely scales it up into hundreds of volts of brute mechanical force, keeping the sensitive controller completely isolated. Binary on-off control handles basic sequencing, but modern manufacturing requires continuous variable data, like fluid pressure, exact temperatures, and specific motor RPMs. To capture variables, we use the 4 to 20 milliamp analog standard. By modulating current rather than voltage, analog signals can travel hundreds of feet across a noisy factory floor without suffering degradation from resistance or electromagnetic interference. A PLC can take that stable analog reading and output a precise command to a variable frequency drive, or VFD, continuously adjusting a motor's speed to match the live production requirements. This network topology maps how these local panels share their data factory-wide. Using high-level industrial protocols like Modbus TCP and Profinet, the PLC streams live production metrics directly to operator touchscreens and central SCADA servers. This final communication layer connects isolated motor starters and scattered sensors into a single unified data environment. Let's map that architecture onto a single real-time action on the bottling line. A glass bottle breaks the beam of a sensor. The PNP sensor sources 24 volts to the input terminal. The PLC CPU freezes that input state, executes its ladder logic, and updates its outputs in under 3 milliseconds, firing an interposing relay. The relay snaps shut, signaling the VFD to halt the heavy conveyor motor instantly, positioning the bottle perfectly under the nozzle, while the PLC simultaneously pushes the updated production count across the Ethernet network to the SCADA interface. Whether you are programming a small water pump or an automotive assembly line, this hierarchy remains identical. From isolated 24-volt power rails up through digital data packets, this physical logical loop is the universal language of industrial automation.